Okay, Assalamualaikum and we meet again. So this lesson is about the analysis of the inductor current for buck boost converter. So I would like to write again the equation, the main equation for that we have derived earlier. So we have this one, IL during turn on is actually equal to V source over L multiplied with T on, and we have another one which is L off, which is V out over L multiplied with T off. Okay, and we also got the equation that relate the input and output, which is this negative D over 1 minus D V DC. Okay, so this is the equation that we have already derived from the previous analysis. So right now what we want to do is to continue the analysis on the inductor current. So assume that this is the waveform. I sketch the waveform of the voltage of the inductor. So T, which is because this is varies with time. So we analysis on during the turn on. So this is the on and this is off. So during turn on, the switch is on, the voltage across the inductor is equal to VDC value. While for the during turn off, okay, the voltage across the inductor is equal to V out value. Okay, but our V out is positive right now here, but since our V out is negative, so we assume that we put here is a negative part. Okay. Okay, so this is actually the waveform for the voltage inductor, and right now we want to sketch the waveform of the inductor current. So the inductor current IL T. Okay, so same, we have the on state and also we have the off state. So during turn on, as you can see, during the turn on here is a positive, right? It's a positive, so meaning that it will ramp from minimum to a maximum value. So this one we call I min, and this one we call I max. Okay, and during turn off, during the switching off, the off switch, so still we have this equation, V out over L 1 minus dt. Even though it is a positive, but it's actually a negative because our V out is always negative. So we have a negative change. Okay, so positive and then negative. So this is IL. So since this is repeated, okay, so this is one period which is equal to our frequency switching. Okay, so since it's repeated, maximum, minimum, and so on. So meaning that we have an average value here. So this one is your IL average. Okay, so to calculate your Imax, so you can just use IL average. And I would like also to remind you that this Imax and I min, the difference between these two values is equal to delta IL. Okay, so Imax is equal to IL average plus IL over 2, and for I min is IL average minus delta IL2. And I would like to always remind that this IL, you can either use either IL on or delta IL off, but make sure that you only use the magnitude only. Okay, so that is actually some of the analysis on the current inductor, the Imax, I min, and so on. But however, right now, how to find this IL average? So we will continue on the analysis on how to derive the IL average. Okay, the IL average can be derived based on the equation between power. So power input, we assume there's no losses in the circuit, so it's equal to power out, where power input is actually VDC, V source, multiplied with the I source. So this is your I source. Okay, in this one is equal to V out square over R. So right now we want to relate IS with the inductor current. So as we from the circuit, we can see that IS is only equal to IL when the switch is on. When the switch is off, IS is no longer equal to IL. Okay, so IS is IL during turn on, during on state only. Okay, so the relationship in mathematics, you can write down IS is equal to DIL. So since IS is a constant DC current, so meaning that this IL also is a constant DC current. So that's why we assume this is actually your IL average. So after we have obtained this relationship, we substitute this into the equation. We finally will have this DIL average is equal to V out square over R, and my IL average will soon can be write down as VDC R. Okay, D. Or if you expand this, so you will have we will expand this into D1 minus D. Oh, sorry. Okay, D, sorry, VDC square over 1 minus D square over VDC R D. So this one you can cancel this one also you can cancel. So finally your IL average is actually D VDC over 1 minus D square R. Okay, so this is your IL average. So next analysis is on the how to determine your buck boost converter to be always operate under CCM. So for CCM, always need that I minimum must at least equal to 0. Okay, so the minimum value is equal to 0. So we insert the equation, which is IL average minus delta IL over 2. So this one I will have your delta IL average is actually what we have derived earlier is 1 minus D minus delta IL okay, so delta IL, so you can use either delta IL on or delta IL off. So for this example, I use for the simplicity and for the synchronization with the slide, we use delta IL during turn on. Okay, so during turn on, my delta IL is VDC over L. So I need to also 2 here. DT. Okay, but DT you can actually T is actually 1 over F. Is actually 1 over F, so I can just put this is also F. So we rearrange this one. So finally we will have okay, so this one will be BDC D 1 minus D R. So is equal to BDC D over 2LF. Okay, so rearrange this one. So my L will be, so this one will be cancelled out. Will be 1 minus D square or multiplied with R over 2F. So since this is the inductor value, the minimum inductor value to ensure it is a CCM, so we put this as a L min. So L min, so we have derived L minimum to determine to ensure that your bubbles in CCM. So actually for to make it ensure that it is always in CCM, so usually the actual that you use should be 10 times than your L minimum. Okay, so I think that's all for the analysis on the inductor current.